What's up, everybody? Welcome to another episode of the Beyond Train podcast. I'm your host, Liam Dalton. Episode 3 today, we have the fall of the germ, history of the terrain model of health. I'm super excited about this one. Pretty much talk about all of my favorite scientists through history. So definitely a more exciting lecture than the last one about the germ, although it was still valuable for sure. So let's get right into it. What are we going to talk about today? We're going to talk about what the terrain model of health is. We've thrown this word out here. We're really going to start building the foundation for that. So we'll touch on that, but in the part two, we'll certainly get into it a little bit more in depth. We're also going to touch on a little bit of health sovereignty today. We're going to look at a few valid versus invalid techniques of studying life. Obviously the terrain model utilizes these valid techniques, whereas the invalid techniques, what we touched on a little bit last time, like electron microscope or things of that nature. But we're going to get more into the like philosophical aspects of it as well. We're going to talk a little about why we blame bugs. Kind of went over that last time, but we'll touch on it again. And then we'll get into the history and finish off with a few of the current scientists still working in this field and really helping move this model forward. In the next episode, it's going to be part two. I had to break this one down when I was making it. Like, I just couldn't stop adding slides. Like, I really had to cut myself off. But in the next episode, we're going to talk about the state of the body. So, kind of the more uh, terrain perspective on what the body is, even down to the cell and what we know about the cell and what we don't, which we'll touch on briefly today. We'll touch on some terrain perspectives in general, where we look at more things like diet, symptoms, immune system, even microbes, and what their role is from this terrain perspective. And we'll cover a couple of the demics, the pandemics, or the um, things of that nature that happen through history and give the alternative explanation that's often not talked about enough. So, what is the terrain model of health? Well, it's certainly not the germ theory versus the terrain theory. And this is really important because when it comes to this fight of germ versus terrain, it's really it's not even about that. The terrain theory, I think, is a misnomer uh, because it's not really a theory. The terrain model it's a framework, right? It's that our external environment affects our internal environment, and the quality of that environment depicts our health, right? And it's the idea is that is as old as time. It goes much further back than just, Antoine Béchamp or 150, 200 years. So we can't get hung up on, which theory is it, this theory, is it that theory? It's not a theory, it's a framework. It's really, you know because even if you're going to try and push a germ theory, it still relies on the terrain framework. So we're kind of just taking a step back, observing the fallacies of the germ theory, and realizing that, oh well, it's incomprehensive, it's based on fallacies and is not sound in nature. And we're kind of just taking that out and getting back to the bare bones of it. The environment is everything. Our terrain is everything. So the terrain, even the word terrain, in French, when Antoine Béchamp, was talking about it, they talked about it as the milieu, right? The middle of the body, right? The terrain of the body. So when we talk about terrain, it's kind of synonymous term with the interior and the exterior environment. Often referred to for the internal environment, but really those are not those are certainly not separate. And that's been known for a long time. Even if you study Hippocrates from the Western lens, he talked about how the body is just a microcosm of the macrocosm of the universe, right? Or even of the world. So, um, the terrain model of health is really more. It's just more than a theory. It's the basis. It's the framework. It's the foundation, right? And on top of that, you can certainly build your theories, such as even a chemical theory of disease or a deficiency theory of disease. There are people in this field who don't necessarily abide by the deficiency theory. They think everything is toxicity because deficiencies lead to toxicity, and perhaps we'll get into that more in the future. But you know, it always comes back to this framework. It always comes back to this, underlying system. So, it's certainly like an alchemical transformation, right? And it comes back to alchemy. We'll always talk about alchemy because that is foundational to the cosmos itself, right? It's the alchemical transformation of the contaminated body to a divine purity, which is health, right? Um, and that's in a more physical sense too, right? Because you can talk about this transformation, this alchemical transformation of the soul, right, of the body, as we just mentioned, and the mind as well. But really, and like it's all connected. It's all synonymous because it's all just one, right? It's hard to have a healthy body without having a healthy mind. They often go hand in hand. So it's about looking at things holistically, right? If you're going to be a miserable, depressed, you know, person, it's going to be very hard for you to become optimally healthy, right? Because, well, you'll lack the motivation to do the things to make you healthy in the first place, but it goes even deeper than that, right? The train framework, we also look at it nourishment, right? It's all about nourishing our bodies in accordance with nature. And nourishment in this sense, I'm not even talking about just micronutrients or macros or, even physical things, right? It's about nourishment is about getting out in nature. It's about being one with nature. It's about being a part of the system that we were created in, right? So it's like it's not solely about the physical when we talk about nourishment. It's about spending time with loved ones, doing things that you love, just getting back to what's natural. So, and the terrain model of health certainly encompasses things like, alchemy, like we've already touched on and we'll continue to touch on as we move forward. Geometry is a big one. Like biogeometry is talked about a lot, and you can see the geometrical um, patterns in nature, like Fibonacci sequences, or even the hexagon shape seems to come up over and over again. And there's sacred angles and there's sacred, you know, it goes so deep. And this is a topic that I've looked into a little bit, but I'm not the most well versed on biogeometry, but I'd certainly love to get some people on and talk about it more and learn more about it because it's just fascinating. And but if you want to learn about it, you just go and observe nature and you'll see it, right? You'll absolutely see it. So again, more fields that the terrain model kind of encompasses is the field of energetics, right? Everything is energy. So we really focus on that life is just energy at its basis. Um, it's all about nature, it's all about life, it's all about light. Like and it gets a little, you think it gets a little spiritual here, but that's what it is at the base. Everything is just energy. What we perceive as physical is at its basis energy. And if you want to study it from a modern framework or a modern way of understanding it, you just look at quantum mechanics, right? If you try and understand what the fabric of reality is when particles act as waves, right? You can get into that and prove it to yourself that way, which I have done in the past. It's kind of my door into it, getting from that scientific, dogmatic approach to things. I went through the quantum field, and it still talks about the quantum field. It's interesting for sure. It's theoretical. So the terrain model health, right? And in respect to that, medicine within the terrain model health is more of an art, right? And healing is more of an art, the healing arts, right? So it's more of a way of life than anything, right? So we really got to focus on that, right? Getting healthy is a way of life. It's a way of being. So that's a really important thing to remember, right? It's all about how we are as an individual and our integration with nature. We really got to get back to Mother Nature, the creator, the cosmos. We really got to get back to it. We really got to, in a sense, worship them, right? We got to really nourish ourselves with their nurture. It's just about living in alignment with nature, with the cosmos, with the creator, right? And that's central. It's all central to the train model of health. and part of that is reclaiming our sovereignty, our health sovereignty, and even in general, our sovereignty, right? We're responsible for our own health, for our own mental health, spiritual health, physical health. We are the ones in the driver's seat, and we need to remember that. And in other senses, right, we got to gain our sovereignty because everything's connected. So even in a financial sense, right, if you're reliant on other people for your income, or you're reliant on the government or whatever it may be for your financial success, right? That can be taken away at any moment, right? So it's tough to be sovereign and not be financially independent. And that's why that's going to be a topic um, on this podcast, not even in a greed sense. Um, and people are certainly prone to avarice, but if you focus on altruism, that's the way forward, right? So generosity and charity over greed. Um, and you must give to receive, and we'll talk about that more too. But another thing in sovereignty you know is the children. They're the future. So I certainly went through a certain amount of unschooling because we're certainly ingrained with dogma since you're very young. So unschooling our children is an important thing, getting them out of institutions, because then you can raise your own kids, um, which is important to reclaim our sovereignty, even to get back into older systems, right? Like even in more communal schools rather than big public schools where the government is the one teaching your child. And I know, like, trust me, um, I understand the benevolence of teachers. My fiance is a teacher and she absolutely loves it and she couldn't be a better teacher. But the problem is your hands are kind of tied when it comes to curriculum and when it comes to outcomes. So it's challenging, right? Because you can go into it with the highest amount of benevolence in the world, but you know, it's part of the system, and that's the problem, right? So it's about getting away from that, right? It's about getting away from these institutions and these large major systems, run by corporations such as government, things like that. And in a general sense, it's about becoming more self-sufficient, right? It's about, growing your own food, or at least connecting with your farmer. Because if the grocery stores go down tomorrow, which may be a little bit of a prepper, mentality, um, a lot of people are going to be out bad. And if you have no connections with farmers, well, I don't know what to tell you. And that's a prepper mentality, but still, like, being self-sufficient and just connecting with your food systems has its own health benefits, has its own mental benefits, right? Like, the more you know where your food is coming from, it builds a sense of gratitude, and it builds this nourishment beyond the physical realm. And local farmers will have more nourishing foods. It's a fact, right? So um and with sovereignty, right, it's about acting in a sovereign manner, but we're still communal, like, we're individuals, but we're still communal, right? We still thrive on our social systems. Now, um you can let it get problematic if the social system is too large, and if you approach it from the top down. You really want to build the one-on-one, the close relationships, right? You want to focus on the smaller communal systems than the larger ones. But like, even when they're, like, going through things like what we went through with COVID, it's about more so civil disobedience, right? Because you get nowhere otherwise. And Thoreau talks about civil disobedience, and that's a great read. Um, but it's about respect. It's about respect too, right? Being disrespectful will get us hardly anywhere, and even this whole divide, right? So and we could go on and on about this. This could be a whole podcast in itself, but and we're kind of moving past that. But it's important to remember moving forward that it's about being civil as well. We are individuals when we're sovereign, but we're also sovereign on a communal base as well, right? So it's important to remember that. It's about that. Yeah, yeah. And we could talk about natural law here. I think we'll save that probably for future reference. But um, yeah, getting back to kind of the bugs and things like that, and are like the health and um, the modern systems really blame the individual, right? We blame our genetics, we blame our biochemistry, and we're told that we're defective. We blame germs, we blame everything except for our lifestyles, and in some ways we do. And when we do blame the lifestyle, often we're told it's the wrong type of thing. So with heart disease, I know I keep harping on heart disease, but this is like the most obvious one, right? Um, we're told, oh, well, heart disease is a lifestyle factor, right? But then we're told to consume seed oils and polyunsaturated fats and avoid animal foods and cholesterol, when quite the opposite is true. So, it's it's important to look at these things, right? To understand even when we're not blaming ourselves, but even that at that point, we still say that, oh, you're susceptible to heart disease and heredity is a problem. And epigenetics certainly doesn't agree with that at all. And that's a modern framework, a modern way of looking at things as well. So and from a Darwinian standpoint, if you're into that kind of stuff, like it doesn't make sense either to inherit diseases. So yeah, I mean, it's all about taking responsibility, in every aspect of your life. You want to take responsibility on every level, and I'll keep harping on that because it's so true. It's so true. All right, so now we're going to move into a little bit more, research-based ideas. We're going to look at some techniques used, kind of in the study of science, and this is, a little more technical, a little more philosophical than anything. So you're looking at valid techniques. What is a valid way to study something, right? Well, I think the first postulate that I would propose is that it needs to be in its natural state. It needs to be in nature, right? In its natural environment. So if you're studying a frog, you know, study a frog in a pond out in the forest in the middle of nowhere and don't interfere with that frog's life at all. You'll probably learn a whole lot more than the frog if you put it in a plastic box in a lab with artificial light and eventually kill it and cut it open and figure out how it works inside, right? You'll learn a whole lot more about the frog and its natural habitat. So observation is a big one here. Now, the problem is that the Flexner report actually touted observation as being an incomplete way of looking at things. And so, you need to go deeper. That was what the Flexner report kind of stated. And there's really, really no need for that. Like we can understand these systems and the cellular systems and biochemical systems, and really that's only pushing pharmaceutical aspects of things, right? Because you're not learning more about the frog by cutting him open, and that frog is certainly not being helped by killing him. And if it's about the frog's health and the frog's well-being, then you need to actually do what's good for the frog, right? And um you can kind of extend that example to more than that, right? You want to ensure that even when you are studying, you're not necessarily diminishing the quality of life for what you're studying to move it forward. And when it comes to humans, it becomes ever more complex because obviously ethics nowadays, which again is not inherently a bad thing, right? But 2000 years ago, 2500 years ago in the Hippocratic era, it was extremely immoral and unethical to dissect people. They didn't do it in the name of God. And they didn't have an understanding for anatomy, and people may say, "Oh, that's problematic." And um but really, like, you know, it I mean, it's kind of hard to tell which way of life was better now or back then. And I guess that's half subjective. And many people talk about the argument that, oh, we died so young back in the day, but we were also fighting wars, and sanitary conditions weren't all that great. So you're living in your own filth, which comes with its own issues. And who knows what the agricultural systems were like. And as we got into metalworks, we weren't careful with heavy metals. So heavy metals were certainly a thing. And there's a large argument that, you know, that life that we've our lifespan has not changed. The life expectancy of humans, the on the higher end is, 120 some now. Well, there are stories where people have lived much, much longer than that. If you look at any indigenous culture around the entire world, you'll find stories of people living longer than 120 years. And, we're often told that they're just a bunch of, tribal savages or whatever it is. But really, like, they were living in accordance with nature. They were living the proper way, right? And we painted them in that picture to diminish their story. So, and to get back to the topic on hand here, um, they observed, they lived in nature, they observed nature. Christ, the indigenous people, they could talk, they could talk to trees, they could talk to animals. They have this amazing connection, right? That's been lost. And so yeah, it's important that for the modern framework that they were painted in this poor lens, which is certainly unfortunate. But there is a they are a strong community, and good things are happening there. So that's promising and that's important. So yeah, I mean, you got to look at things in their natural environment. Even so, Weston A. Price studied indigenous people and their diets, and we'll touch more on Weston Price there in the coming slides. And he studied these natives in their native environment, living their native way of life, and they had little to know. Well, he studied from a teeth perspective, and they had little to no facial deformities or cavities or even disease otherwise. So, you know, it's it's important to look at them in their natural environment, because when he studied those same native groups in the modern environment, well, they had all these diseases, they had dental deformities, they had dental caries. So, uh, a co-founding factor. That's a variable that's never controlled in studies nowadays. When we study rats in the lab, right? So we don't study rats in their natural environment, which comes with its own issues. And they're like, through history, like, people have thought about things logically. They've meditated on topics. They've really meditated long periods of times and thought about it and talked about it, from a logical point of view, and even try to dismantle their own arguments, right? That's something that's not done as much anymore. We don't necessarily ponder on our ideas as much as we used to, because obviously it's not as the modern framework's not as conducive to thinking and really thinking things through logically and rationally as it used to be, right? So this active thinking and this philosophizing, using this logic and rationale is so important. It's so important to working through these concepts, because if you can work them through verbally, right? You can do that. And accompanied with observation, it can be very powerful. It can be very powerful, because there are laws to nature. Nature has its laws, and we can understand. We have understand them. We come from it. It's within us. The understanding is within us. We've lost it. That's the problem, and we're trying to regain it from an arrogant standpoint, where we think that we know everything already, right? And we think that our synthetics are mimic nature, are just as good as nature. And obviously that's not true. And so we could touch on things like, microscopy or light microscopy or dark field microscopy as valid techniques. Now, this may be argued, so I'll touch on it briefly, but you know, these seem to not necessarily disrupt the natural environment as much. But the problem is, even if you're studying the blood in a dark field microscopy, you're still putting it on a slide, right? So this is why I put arguable here, because the microscopy can certainly allow us to see what the naked eye can't see, but then at what point is that really what point is that even necessary, right? Because we've lived well without that. So, but these techniques seem to come to more natural conclusions than things like electron microscopy or things like that. But it's tough, and there is live blood analysis, which may also be good, but then still there's the light, and there's so it's difficult. It's a difficult argument, right? So, and it depends, right? Because within the modern framework, modern solutions are necessary. So if we're going to try and bring someone from a really diseased state back to a natural, healthy state, we may have to go in with more rigorous techniques. So That's why I put arguable there. It's certainly it's not it's not 100% natural, right? If it's on a little glass slide, I mean, it can be art, right? It can be art. We'll leave it at that. Now, for invalid techniques, right? Looking at dead matter, and maybe this is something I should have mentioned in the valid techniques, right? Looking at things alive. But if it's in its natural state, it's likely alive. I mean, you could study dead things and only gather a certain amount of stuff from it. But, dead things certainly don't act like live things. No one's going to argue that, right? A decaying tree doesn't act like a live tree, right? So it's important to look at live matter. So, and this is as old as thought, right? Killing a tissue and studying it is not the same as studying a live tissue. And that was the idea behind this Hippocratic, or not necessarily Hippocratic. It was more the ethical way of not dissecting individuals, right? In the name of, piety. Um, so, it's not a new idea, right? The live tissue, no one assumed that the dead tissue would act as the live tissue. And they even thought, the dead tissue may not even look like the live tissue. So what's the point of even looking at it? So that was the idea there back in the day. And we could elaborate on that, but we'll move forward here. Things that disrupt this live matter is things like drying. You can't dehydrate something, you can't dry it without it being alive. Everything needs water. Water is essential to life. There is no living thing without water in it. Freezing things, that obviously alters the water in the body as well. It expands it and freezes it in motion, which is problematic. Staining things with metals obviously disrupts the chemistry of things and the weight of things, and the frequency of things. So it goes fairly deep here. And beaming things with unnatural frequency. So what did I just describe here? Electron microscopy. But adding any exogenous chemicals, it really disrupts things. It really just you know it's just going to mess with it, right? If you look at things from even a biochemical standpoint, adding any exogenous chemicals is going to disrupt that delicate equilibrium that they describe in chemistry. So removing things from the natural environment is certainly invalid. It's certainly invalid. You have to study things in its natural environment. That's a variable that's never taken into account. And Harold Hillman, who we'll talk about here, proved that these factors actually change the nature of living tissues, change the structures, and changes the angles and everything. And we'll touch on this more. We're going to talk about Harold Hillman here, but he proved scientifically that dead does not depict life. That even freezing, drying, dehydrating, and staining it does not give an accurate representation of what it is when it's alive. And so really this comes down to the death science. It's more of a death science. We're more focused on things when it's dead and in its unnatural state than when it's alive and well and thriving and optimized. And so that's a poor distinction that modern science living on. Right. So, and the problems in modern science is it's really, a study of effects. It's really a study of effects. And we're not looking at the cause of things because we're looking at well when we do this, what happens, what effect, right? We don't really care about the cause. It's interesting, right? Like it's like we don't know the cause of cancer, but when we do studies on mice, cancer studies on mice, we can induce cancer in mice, no problem. And we sit here and say, oh, well, we don't know the cause of cancer and blah blah blah. It's like, well, we could certainly create these diseased in, like, animals. So how are you going to sit here and tell me that we don't know the cause? But they just want to know the effects. They want to know, well, we're going to test these drugs and see if we can't not reverse this with more with more cancer causing things, chemicals and radiation, whatever. The reductionist way of looking at things is so problematic in modern science. We reduce everything. It's almost the goal of modern science to reduce things, and not even reduce things in a way that's understandable, but we reduce things to not even to simplicity, but just to, like, to the material way. We reduce it to chemicals. We reduce it to not living in accordance with nature. You know, we reduce it to one field. We reduce it to cardiology when we need to be studying the whole body. Reductionism is almost the opposite of holism, right? We need to be looking at things as a whole. Obviously, we talked about in the last lectures, the literature is absolutely just polluted. You could cherry pick any study, you could cherry pick them and come out with pretty well any idea that you want. So it's not enough to just look at the literature nowadays, in my opinion, because you can really come to any conclusion, and this is obvious because there's, hundreds and thousands, of scientists out there, all with different opinions. Well, they're all scientists. We've also split the fields, which is absolutely problematic. Like I said, cardiology or endocrinology, or, it gets so specific now that we've divided these fields. We've reduced it to one field. And obviously that's problematic because we're getting away from the holistic model. We're getting away from the whole body working as a body, right? We got away from the body and we're going to systems and organs and cells. And even at university, you can take these extremely, extremely specific areas of study. And it's just like, how useful is this for people other than the pharmaceutical companies? So, you know, the peer review process, we mentioned that before, it's just an echo chamber. The referencing process, even, we're paraphrasing what other people are saying, and the uncertain conclusions are problematic. So there's obviously a lot of vested interests in modern science. It's very politics based, greed oriented. Greed has certainly infiltrated the field. Look at the money, find the truth. It's very, very simple. And this whole field of half truths where, we kind of we observe the germ at the site of disease, and yeah, the germ is there and it plays a role, and that's the half truth. And then the half lie is that it's the cause of disease, right? So, and that's within everything. It always seems to be a half truth because it's easier to convince you if it's half true, right? If it's fully a lie, it's much harder to convince you. And so the facts of the matter are that dead matter does not act like live matter. The material construct of the body is flawed. We we got to move past that, right? We're an electrical body, we're a natural body. We have to look at the whole body. Um, in brief, viruses never been found in the fluid of a sick person. Um, it's just these samples they take is just this big conglomerate, this big homogeneous mixture of a bunch of stuff, and it's all made of the same material. It's all organic. It's all, carbon, oxygen, nitrogen. um it's very hard to distinguish from one another, right? And so even viruses, they even say this, that it's too little to see in an entire sick person. In an entire sick person, there's not enough virus to be able to see, to be able to take that virus out and isolate it, right? So it's just very difficult when studying these viruses, especially like, and we touched a little bit more on that in the past, and in the past episode there, episode 2. um and the viral debate, like it's just ridiculous. And it's very difficult too. And Dr. Andrew Kaufman does really great work in this area, and especially in its relation to exosomes, which we'll touch on more a little bit in this episode and a little bit more in the next. But just the fact that viruses have never really been isolated. They've never been in true isolation, right? And that gets back to the definitions we talked about, because filtration obviously is not isolation. And of course, Koch's and Rivers postulates have never been obtained for any microbe. You can go verify this self, and if you find a study that has satisfied them all, that you think have satisfied, send it to me, please. I would really, really appreciate to read that, and I know a lot of people that would. No published study even attempts Koch's postulates directly from viral filtration, or from a bacterial smear, and so that could be the closer way, right, of looking at things. But they can't, because there's too little virus or bacteria to produce a disease or a symptom in an individual. even though there's too little virus in an entire sick person to isolate directly from a person. So it's always cultured, it's always in the presence of other toxic chemicals, and I'd urge you to refer back to episode 2 where we touch on this a little bit more, or go and look into Andrew Kaufman's work. He's really pioneer in the field there. And of course, why do we blame bugs? Well, they're at the site of infection, right? Correlation in this case equals causation. And this is just the materialist way of looking at things. It's the reductionist view. They're there, so they must be the cause of disease. But no one claims that firefighters are the cause of fires. No one claims that maggots kill deers in the woods, even though maggots are present on every single deer carcass, or you know, it it's just difficult, right? So we really just reduced the whole germ debate to that. Microbes are more like biological healers. They're more like the microbe garbage men, right? They're the ones there cleaning it up. They're the ones there putting out the fires. They clean up our milieu, they clean up our terrain. That's what they do in the external environment. Microbes, they're decomposers, they're saprophytic. They break things down to its natural building blocks to be able to be utilized again. That is the pure purpose, right? They purify our body from contamination. They purify our body from dead, diseased, dying tissue or matter, and bring it into a lifelike state again. They are they are divine in that sense. It's we've we've painted them in such a poor lens. It's kind of sad. Even the idea of a germ, what like before a germ um was associated with microbes, a germ is it's a seed, it's budding, it's growing, it it has all of the necessary information to be able to create a plant out of it, right? It's a germ, germination, right? So that's the original meaning, and we've certainly taken it away, and it's a little bit bastardized now, but um yeah, I think that's important because, when we start talking about the pleomorphic cycle of germs and how they're more cyclical, and you know, they can morph into different shapes and different states, and um it's important to remember this, what a germ is. If you do forget what it means with microbe, think of it in the plant, from the plant perspective, from the plant world. And obviously the bugs, microbes, they promote the victim mindset, right? Oh, well, I'm healthy, but I just caught a little sickness, right? So it gets us away from truly optimizing our health too. We need to really take responsibility. If you're getting sick and you're having these detoxes, there's something within you that needs to be out. So it's important to look at these symptoms as a sign of, okay, well, maybe I need to be a little more healthy here, right? It's not about the victim mindset here at all. Okay, now we're going to get into a little bit of the history. So pre-germ, pre-germ. Well, there was that one guy, Fracastoro, who talked about a little bit about the germ theory, but could certainly be interpreted more as a chemical theory. But pre-germ, everything was terrain. There wasn't a terrain theory. It was just this framework that I was talking about earlier. It was all about seeking balance within the environment that we're in, our internal environment, our exterior environment. Every school of medicine around the world, Eastern medicine, Western medicine, even Hippocrates focused on balance, focused on the terrain. Um, they even, it was even thought of between the germ theory of disease and them discovering the microscope. There was this idea of spontaneous generation, that, life just kind of came to be. So that, or even disease just, came to be randomly. It's not an absolutely new idea, um, as per our known history books. So this victim mindset's not new. This spontaneous generation was kind of the way of having this victim mindset. And obviously spontaneous generation was disproven by Antoine Béchamp, and it was fraudulently claimed as their own work by Louis Pasteur. Um, and we talked about a little bit about that in the last episode too. But even the germ theory of disease is almost gets back to the same idea of spontaneous generation. It's kind of funny how Pasteur, was known as disproving spontaneous generation and then created a spontaneous generation theory, right? Disease just happens. It's just random. It just randomly occurs in the body. You just catch the thing. It's almost spontaneous. It's almost spontaneous generation. It's certainly spontaneous disease. It's just kind of funny how that happened, how he claimed to, have this major feat in science and then kind of just recreated it again. And anyway, it's just a little ironic, but pre-germ, it was all ancestral medicine. It was natural medicine, right? It was herbology. Um it was not allopathic. It was holistic. Everything was very holistic. It was always the terrain and its integration to the cosmos. It's always internal, external, milieu. Even the Hippocratic era, right? He talked about the humors, and obviously he's flawed in his own sense, but you could pick apart pretty well any theory placed on top of the terrain model of health. You could pick it apart, right? And so obviously they all have their flaws, but um, yeah, I mean Hippocrates talked a lot about balance too. So it's not even an absurd idea in the West that balance has not been a thing, right? So it has been around for a long time. Even though Hippocrates is the basis for allopathy, but obviously his work's been bastardized and touted as, Abraham Flexner killed Hippocrates in the Flexner Report, absolutely killed him. Um, pretty much put his work to rest. And obviously, we don't even talk about Hippocrates in modern science at all. Even though you can put off his work as being just the humors, but it was certainly more than that. Not even that Hippocrates was the best physician out there in history. And so, interestingly enough, Florence Nightingale was likely one of the first people to kind of attack the idea of a germ theory. Um, and this was in 1960, and it was well before it was mainstream. And Florence Nightingale is a great one to study because she studied a lot about these symptoms and its relation to disease and how we kind of just group these symptoms together to create these diseases, which comes with its own problems, right? Because then, the symptoms, I think she understood more that the symptoms are the body's natural way of healing, and grouping them up and naming diseases is not necessarily the most helpful thing. Okay, so first off here we have Claude Bernard, 1813 to 1878. He was a physiologist. So he was definitely pre-Pasteur in his work, pre-germ theory. And he had ties with the emperor as well, Emperor Napoleon III, who Pasteur also did, who met with him. And it's claimed that, Pasteur kind of told him that he was going to create something that he could make a lot of money off, especially in relation to disease. And he said the germ is our ticket here. It's our ticket. So Claude Bernard, he had ties with the emperor as well. He obviously lost out to Pasteur. But his work is very important because he really established the scientific method in medicine, right? And it's rather sound and logical, and I think it's been lost in many ways. Um, it's certainly based on experimentation and observation. I don't know how much he mentioned it being in a natural environment. I think that's what he was getting at, but it was certainly not really invasive procedures or even creating all these variables and taking things out of their natural state. So he was really known for that, and some of his remarkable works that he was also known for was pancreas secretions as a process in digestion. So he kind of figured that stuff out, like the enzymes secreted by the pancreas. He also understood the glycogenic function of the liver. So those are the two things he was really known for. But really, why the terrain theory, or the terrain model of health, is kind of based on his work, is because he was really known. He kind of coined the term for the milieu intérieur, right? So the internal milieu, the internal environment, the internal terrain. And this kind of got taken on by the mainstream as homeostasis. And that's kind of the mainstream way of, looking at things holistically and looking at things as the internal environment, right? It's all about homeostasis. It's all about balance within the body. And that's kind of the mainstream's ticket to holism. He kind of replaced the Hippocratic idea of humors, which wasn't necessarily a bad thing. It was a little bit dogmatic in itself, and it's unbelievable that it's been around for that long. I mean, Hippocrates really had a serious influence on the West, so it's not that absurd, I guess, to think. But you know, Bernard, his initial focus was on the blood, and eventually moved to the whole body. And the blood is a very, very interesting topic, and much can be told about the blood. There's a lot of people out there who focus mostly on the blood as its relation to the body. Some may even say that the blood is a microcosm of the body, as it contains absolutely everything. And Bernard's work led to works of Antoine Béchamp, who we're going to touch on next, Szent-Györgyi, homeostasis, ground substance, and the extracellular matrix, and much more, right? So he was really foundational in even modern science. So, he was very, very, very influential in both areas, in the holistic field and the allopathic field. Okay, next, Antoine Béchamp, everybody in the terrain field's favorite scientist, 1816 to 1908, lived a long life. And Antoine Béchamp really, from a scientific perspective, not enough can be said about this man. He was a man in the community, professor of medical chemistry, pharmacy, physics, toxicology, and chemistry. He was a master of pharmacy. He was a doctor of medicine and science, and he was a true scholar who dedicated his life to science, even maybe a little bit too much, right? As his family might point out. But, um, there's real no basis for that claim. But anyways, to focus on his work, he really focused on the pleomorphic nature of microbes and really, really looked at these things called microzymas. And this is going to be a kind of a more central aspect of this model too. Microzymas being the fundamental unit of life present in all living organisms. Yeah, so I mean, microzymas, they kind of give rise to these different forms of microorganisms. So they're kind of like the germ, they're the basis, right? They're the seed, and they're kind of everywhere, right? So there's these little minuscule bodies. And so the pleomorphism is another central thing that I really want to drive home here. Is kind of just the changing nature of microbes, right? So microbes can change their form and adapt to different conditions. So this is the way that microbes kind of develop in the body rather than being externally caught. We have the basis to create any microbe in the body. So when we're doused with any toxicity or poisoned with any toxicity or deficiency and have these dead tissue, our body has the innate capabilities of growing the correct microorganism to deal with the situation. So, and that's the idea of pleomorphism, right? It's completely dependent on the terrain and the environment. Some people say that microbes seek their natural habitat. The pleomorphic model kind of says that, microbes just grow into their natural habitat. They kind of just develop within it because they have the microzymas present. And getting back to the dark field, this is observable through dark field microscopy, and it's been observed quite a bit. Quite a bit. You can see these minuscule bodies, smaller than cells, much smaller than cells, probably more so on the level of viruses, but not I think smaller than viruses, but not a replacement for a virus. That confused me for a long time. A microzyma is not a replacement for a virus. A virus is really an extracellular vesicle. It's really an exosome rather than a microzyma. The microzyma is really the bud. It's really the germ of. It's really the seed of microorganisms. And so, Antoine Béchamp, he really highlighted the importance of the internal environment or the cellular terrain in determining health and disease. So he really worked off Bernard's work there, and you know he really looked at the internal environment as being a direct representation of the external environment. Like it's very like there's no distinction. It is the relationship. It is that's it. They work on a hinge. And so that's really, really, really important to drive home. And so importantly, in the 1890s, you were not allowed to publish anything about pleomorphism. Thomas Rivers, I think, was a major proponent of this, but I think his work might have been a little bit later than this. But regardless, 1890 was kind of the threshold for, you weren't allowed to talk about this stuff anymore in medical literature. But before that, it's well documented in the literature quite a bit. And because the way that things were done back in the day, it was more like sending letters to the medical establishments to kind of publish their stuff rather than this IMRAD, this introduction methods results discussion format that has to go through all these boards. You kind of were just an established scientist, and you were publishing your work, and that's why it's so well documented that Louis Pasteur stole of all of Béchamp's ideas. So um, well, not maybe not all, because Antoine Béchamp certainly didn't think that germs cause disease. Um, yeah, Antoine Béchamp was kind of Louis Pasteur's nemesis back in the day. Yeah, they did. Louis Pasteur certainly didn't like Béchamp. And I mean, Béchamp was probably not too fond of Pasteur because he stole his work and would just deny it. And did Antoine Béchamp very dirty. Okay, so more on the Microzyma here. Antoine Béchamp is kind of the first one that really talked about this Microzyma, and that's why we're going to highlight it here. So it's a pleomorphic organism. It's ad ovo and semen, which means that it's at the basis of life. It's the beginning and at the end of every living organization. It is the fundamental unit of life. It is the Microzyma is the egg and the semen. It's the egg. It's everything, right? It's present in all parts of living tissue, blood, milk, liver, everywhere. It's in plants as well. He did a little bit of work on that as well. So basically, Microzyma kind of it develops into these vibrios, and in the right condition, bacteria. So it's kind of I don't know if Antoine Béchamp said that it was linear, but it had this progression. And I know Gaston Naessens really proposed that it was cyclical. And Gaston Naessens also proposed that they can evolve into fungus as well in the later stages of disease. But the beauty of it being cyclical is it always comes back to the Microzyma. So even when the disease is dealt with, eventually it comes back to the Microzyma. So these Microzyma, they kind of undergo this Brownian motion, sorry, and it's seemingly random, right? So it's a little bit like, but we know that nothing is random, of course. And even in the mainstream literature back in Béchamp's days, it was initially classified in the plant kingdom, as all microbes were. They were named by the mainstream as Bacterium punctum, Monas crepusculum, Coccus, Micrococcus, um, pointed microbe, and spores of schizomycetes. So if you're really looking at the old literature and really delving deep into the stuff, you can kind of use these terms synonymously as long as you're in the right era, but you'll kind of get the gist of what they're talking about too. Um, Interestingly enough, in the mainstream view of things, it was believed that these microzymas entered by means of penetration. So kind of they were still trying to, before they got rid of the term microzymas and pleomorphism, they really tried to push it into the germ theory, right? Which obviously it just didn't fit, and that's why they had to get rid of it and stop talking about it because that was the only way that they could continue to push this half truth of the germ theory. And yeah, I really do think the renaming of the of Microzyma to these other names was kind of to remove Bischamp's contribution because Béchamp was not a fan of the germ theory. And so, shifting his discoveries into the main, like that fits into the mainstream model was kind of the point here, in my opinion, right? And so Antoine Béchamp basically did a lot of work in fermentation. And this is kind of how he found out about microzymas, where he kind of used this one experiment that hit it home really well, using natural chalk, which contain these microzymas, versus the synthetic chalk. And essentially, through the fermentation, if you use the natural chalk, you would you would a fermentation would occur. It would ferment, the sugar would invert, or whatever means he was using. But in the synthetic chalk, it wouldn't, because there were no microzyma present there. So these microzymas are really kind of they're everywhere, just like bacteria is everywhere. It's on every surface, right? And it is important to say that they are able, like, there are methods to inhibit the growth of microzyma too, and that is kind of problematic in itself. Um, And another thing to note was that these microzymas really develop. Béchamp spoke about how these microzymas develop at a certain temperature, like 37 degrees. I might be off a little by a couple. I think there's a specific number, but and this kind of points towards why a fever may be necessary for healing, right? To allow these microzymas to kind of grow into that bacterial state to be able to clean house, and then back to the microzymas once the fever's gone. So even inhibiting that fever can be really problematic. And we'll come back to microzymas all the time. It's really central. There'll be a lot of people on this podcast hopefully talking about that stuff, because that's really kind of the pleomorphism is really central to this concept. And it is, the pleomorphic theory may be more of a theory, but it certainly seems to be grounded in the cyclical nature of things, um and things of that nature. So we'll touch on that a lot more here. But moving forward, we have Rudolf Virchow, 1821 to 1902, and this guy is kind of touted as the father of modern pathology. He was a plagiarist. He did plagiarize one of his co-workers' works. So obviously that's problematic. And he was a politician, very good politician. Um, Now Virchow is, he's kind of an interesting man, right? Because he's talked about much in this side of the literature here, and um, but really he didn't really push forward too much the idea of the terrain model of health. Um, but it was very interesting, the approach that he took. And he was certainly for the freedom of science. So he was against Darwin. He was completely against Darwin. Not to say that Darwin's completely correct, but he was anti-Darwinism, and this led to his work on the liberty of science in the modern state. So he was really for freedom, like scientific freedom, which is important, right? So at least a politician in that era was for that. He certainly emphasized the idea that disease originates at the cellular level, which was an interesting concept at the time. And his primary investigations determined the cause of disease and the effects of drugs at the microscopic level. So that's what he was really concerned about. He believed that diseases came from activities inside the cell, not necessarily from outside pathogens. So this was kind of wasn't necessarily a center of his work. Um, because yeah, I have a little quote here from him. Uh, he says, "If I could live my life over again, I would devote it to proving that germs seek their natural habitat, diseased tissue, rather than being the cause of dead tissue. In other words, mosquitoes seek the stagnant water, but do not cause the pool to become stagnant." Um, and so that kind of is the quote. I think, well, it definitely proves that he was for the terrain model versus the germ theory. Maybe he was more for a terrain theory in a sense, but um, you know, nevertheless, he's a very interesting man in this field, and certainly maybe he was influenced a little bit to go the other way. You never know on the political level. Um, he really thought that another interesting thing is that he really thought that epidemics were of social origin. So he thought that these epidemics could be combated politically and not medically, which is kind of interesting, right? Which doesn't necessarily bode well for how things are now because, um, well, certainly, the last pandemic we saw with COVID was handled politically and not medically. So, certainly his work could be interpreted either way. Um, but interestingly enough, he opposed Koch's hand washing and antiseptic practice. He wasn't for, removing all the germs on your hands, right? So this is why it's kind of interesting. So he kind of took this political way of things, which, is certainly not necessarily an absurd idea, but it can be interpreted in different ways, right? And another quote here, he says, explorers of nature recognize no bugbears other than individuals who speculate. I'll leave you with that. All right, next I'm going to throw in Weston A. Price here. He was alive in the 1870s till 1948. He was a dentist. So his focus was teeth. His focus was the mouth, right? So his major work was nutrition and physical degeneration, which included his life work, where he essentially traveled around the world and worked with indigenous populations from around the world. I think 12 or maybe 13 different populations, and essentially looked at their dental structure and general health. He also looked at the generational health of things. So essentially, what he did is he would find these untouched um, indigenous populations, and there would be the same indigenous populations would have some in the untouched areas and some in the modern areas, or would even look at some of the more untouched areas that lived near a railroad, right? So they could get deliveries of the modern foods, right? Like jams or sugars or grains or whatever it may be. And so essentially what he did is he looked at these natives that were untouched, looked at their teeth, looked at cavities, looked at their dental structure, and like I said, their general health, looked at the native living the modern life and looked at their teeth and their dental structures. And what he found was, they had poor developed dental arches and they had a lot of cavities in this modern group. And in the control group and the natural, native group living their natural way of life that they've lived for thousands of years, they had extremely low incidence of cavities, maybe one or two on average. Whereas in the modern group, they really had, they could have anywhere from, 20 to 60% of their teeth being having cavities. And obviously in the indigenous group, they had, no dental deformities at all. And so the deformity of the face, he kind of brought it down to the generational health, right? So the health of the parents kind of depict the health of the child's dental structure. Because he found that even in the modern group, if you were living in the modern way of life and you had dental deformities, if you went back to living the native way of life and had children, your children would not have dental deformities. And cavities is basically a more individual thing. It's that cavity incident um, it doesn't really dictate the health of the parents at all. That's more in the birth defect of the dental structure. So his kind of focus was on diet and nutrients, although some people say that, they had the people living a more, native, their natural way of life. Um, we're living in more smaller communal systems, family oriented, ate with loved ones, connected with their food systems. We're out in nature all the time. So, there's this argument that it's more than just nutrients, but for the purposes of his book, he talked a lot about vitamin A. And vitamin A, he used cod liver oil to produce a lot of results in people, which is really interesting, right? So it's not absurd that, nutrients certainly play a major role. But, this vitamin A, he would give it to people and they would end up having less birth complications, when they were well nourished. They had much less miscarriages. They had much less, issues during pregnancy. It was more enjoyable, quicker labor, things like that. And the kids came out and had much less deformities, right? So that was kind of his study. I highly I like his book, Nutrition and Physical Degeneration, is one of the most important books for absolutely everybody to read. I really think it's central. And, you know, he touched a little bit on tuberculosis and how natives living in the native way did not have tuberculosis whatsoever. And the ones that living the modern way of life would have tuberculosis. So, that he kind of questioned the germ theory of disease quite a bit, which is important. But his focus was certainly on nutrients, and I could not recommend this book enough. It's so enjoyable to read as well. It's really an enjoyable read. It's not too dense. It's not too, overly scientific, right? Because he kind of compiled all of his scientific works and placed them in each chapter. So he even talks about the ways of life of the indigenous people and their hunting and their traditions and things like that. So he paid a great homage to the native groups, which was absolutely great to see. He painted them in a good light, which is needed. So highly, highly recommend his book, Nutrition and Physical Degeneration. Absolutely phenomenal book. You can gather so much insight from it. I would read it, reread it 5 times. Okay, next here we have Günther Enderlein, and he was alive from 1872 to 1968. Günther Enderlein dedicated his life to pleomorphism, symbiosis, and the cyclogeny of microorganisms. So the thing about Gunther Enderlein, and I haven't read too much of his work, to be quite honest with you, his work uses really complex terminologies. So he really kind of changed the names of a lot of things. So it's kind of difficult to read and really understand unless you're really studying his work in depth. And if you're a practitioner, it's worth getting into because Enderlein he was definitely up there. He definitely had a great understanding, and it was all certainly based on Béchamp's work. It was based on Antoine Béchamp's work, definitely. So Enderlein did a lot of work, live blood analysis and dark field microscopy. So he looked at the blood. He was a big blood guy. Um, he proposed that all illnesses can be treated by altering the internal milieu, which he called the mesenchyme. The body fluids and the cells, right? So that was kind of his description of the internal milieu. He proved that microbes can develop not only by division. So that was a major part of his work, right? That these microbes can, almost evolve and change states rather than just, the division in their moving forward, in their progression, I should say. So he proposed that each microbe produces an organic acid to promote its upward morphing or evolution in the pleomorphic cycle. So he kind of getting really technical with things, right? So if you had this certain microbe, it could produce this acid, and in this acidic state, it would um, it would promote the evolution, right? It would promote changing nature of yourself, right? So it's like, you know, you it's like you're setting yourself up for growth is the slight analogy I could use. And Enderlein was a big fan of isopathic remedies because they, penetrated really deep into the metabolic processes of the internal milieu. And so these isopathic remedies were kind of to help the microbes along their cyclogeny, so to kind of help them move through this cycle of pleomorphism. So they like, he really thought that these microbes were apathogenic symbionts, that they were there to help. And so that's why he wanted to help. He kind of helped them through. So he kind of helped the microbes develop, clean up, and detox, or drain the microbes perhaps at the end. Um, so yeah, I mean, it was kind of these isopathic remedies were kind of accessible for the body to detox and remove these things through the immune or lymphatic pathways. So that was kind of the end part of it, right? it's all about cleaning it up, but it's also about getting it out, right? So if you're stagnant in your own lymph and you're stagnant in your own blood and everything in your body is stagnant, if you live a stagnant lifestyle, a seated lifestyle, you're not moving your body, it's not conducive to your drainage pathways. So it's one thing to put the garbage out at the curb, but if the garbage man's never going to come and take it away, well then, what's the point? The garbage man can spend all day at the bottom of the curb, that garbage is not leaving anywhere. He's got to get it, take it away, right? And that's the point, right? So the microbes got to come in, clean it up, but they got to take it out. They got to go. So that's really important to note because you really got to ensure your drainage pathways are good. And we'll talk about more, concrete ways of doing that too. Um, Even on like on Instagram, it seems to be a little more concrete and pragmatic there. So kind of giving quick tips rather than these long-winded explanations and behind everything, right? So go follow me beyond.terrain on Instagram if you want to know that. Interestingly enough, Enderlein recommended a vegetarian raw diet to heal disease, raw being the important note here. Is raw vegetarian or raw veganism sustainable in the long term? I would argue not because of the lack of nutrients naturally occurring, but it's certainly you're certainly able to see results. People see results in the short term on these raw diets, and raw is really the way of detox. It's really important for detox. Okay, next here we have Royal Rife, 1888 to 1971. He was an American inventor, invented this microscope that you call the universal microscope, 60,000 times magnification. Um, Now obviously he was an amazing inventor. This is a very, very impressive thing to invent, and obviously is not a widespread thing because he was able to view live viruses or bacteria, what they call viruses, but he was able to see what that was. And so basically he noticed that each microorganism kind of had a unique frequency or what he called a mortal oscillatory rate, MOR. And so where Rife kind of where he shined was he hypothesized that exposing microorganisms to their specific MOR, it was able to destroy them without harming surrounding healthy cells. So he was kind of able to help that, the drainage pathway along its way. Now, I kind of, and perhaps I don't understand Rife's work enough, but when he says things like destroy the microbe, it's hard for me to kind of get on with it. Now, I know people in the field absolutely love Rife, and that's why I think that I'm misinterpreting it slightly here. Um, and what I think is the answer is that, it's not about destroying every microbe. It's about destroying the microbes that are kind of overstaying their welcome. So perhaps if you're not draining properly and, you're not getting through that cyclogeny enough, it's about it's about like it's about getting that out. It's about detoxing that. So that's kind of my understanding. I'm not 100% sure. You should look into more Royal Rife's work. Dr. Bear Paul Lando does a lot of talks a lot about him. He has a couple podcasts dedicated to Royal Rife. So I'd urge you to go check those out too. He does the Alpha Vedic podcast. Um, and he's just amazing. You should listen to all of his podcasts. So, Royal Rife developed a frequency-based therapy known as the Rife machine. He treated numerous conditions, including cancer, tuberculosis, and syphilis. And, Rife's research papers and equipment were lost after he died. And they were likely destroyed or probably hidden and studied. You never really know what the deal is with this type of stuff. So it's kind of difficult, but obviously his work's not around too much. And there are people with Rife machines, and that's a whole topic in itself. People, it's certainly been ostracized by the medical field. Okay, next year we're going to talk about Gaston Naessens, 1924 to 2018. And he was a French biologist, developed a specialized dark field microscope called the somatoscope. And so he kind of rediscovered these subcellular particles and he called them somatids, which is synonymous for microzymas. And he observed these within the blood cells of all living organisms, within the actual cells of the blood, interestingly enough. And he described these somatids as being dynamic and could undergo various stages of transformation, which is pleomorphism. Naissance believed that somatids played a central role in health and disease. He theorized that certain factors could trigger the transformation of somatids into pathogenic microorganisms, leading to the development of various diseases. So, again, it's kind of the same story over and over here, with different, slight different interpretations, but all around the same general idea. Now, Gaston Naessens developed a drug, 714X, which is a mixture of camphor and mineral salts, and it was an injection. And he claimed that it could stimulate the immune system and had a lot of success with it and cured a lot of cancer. Cured a cancer in a young boy, I believe. And this is where the double standard kind of comes in because when you look at the germ theory of disease, you look at Edward Jenner who inoculated a little boy, um, versus Gaston Naessens who was locked up and ostracized by the medical community for doing something unethical, um, which sure I can agree with. It's just the double standard of things. And it's not like Gaston Naessens didn't have positive results. So that's the problem. He had a lot of legal disputes. You don't hear too much of Gaston Naessens, but certainly did a lot of great work. And I'm not. He has a book on 714X, which I haven't read. But it's on the reading list for sure. And so, I'm not sure about the workings of it. That's just kind of what I've heard about him. And so, if you're watching on the video here, here's a little bit of a picture of the somatidian pleomorphism. You can kind of see the somatids and their development, how they go through spores into bacterial forms, into rods. They go into microbial globular forms where they burst into yeast and then ascospore form. And if there's a poor milieu, it could go back into these, these larger um, houses for the microzymas, I believe. But it can also develop into mycelium form. Um, and if you have a proper milieu, you can really go back to the somatids, to the microzyma back to start. So if you're watching the video, please have a look here on the screen. This is kind of an interesting, it just shows the psychology of things. Again, I'm not a somatidian doctor, so the cycle, we can look at it and observe it, and it's interesting. I kind of understand this theory, but I'm not one to interpret it or really be able to work through this in someone's body. Interesting nonetheless. All right, next here we have Albert Szent-Györgyi, and we're kind of going back a little bit here, but we're kind of switching the field. So we're talking a lot about pleomorphism. We're talking a lot about um, microzymas and things of that nature, microbes more so. We're going to kind of shift to a little bit of cellular biology, or this kind of the structures or the making of like the yeah, I guess the structure of the body on a smaller level, right? So Albert Szent-Györgyi, he was a biochemist, Nobel laureate actually for the discovery of vitamin C and his work on cellular respiration. He built upon Moglich and Sean 1938 and Jordan 1938 non-electrolytic mechanisms of charge transfer in living systems. So he kind of built upon these three on their work, especially considering like the cellular respiration area of things. So he proposed that proteins are kind of like semiconductors or porphyrins. We'll touch on that more, what a porphyrin is, on the next lecture. But that the idea that these proteins, are able to kind of hold and carry and move this charge is central to his work, right? Because proteins are very abundant in the body, and the fact they're electrical kind of allows us to build upon this structured aspect of the body beyond the cell. So he pointed out a lot of biochemical fallacies. Albert Szent-Györgyi was great, logically, rationally. Um, he thought that the billiard ball theory of chemistry is absolutely flawed, that all of these chemical reactions can just happen in our body naturally, and they all just kind of flow together and go to the right places at the right time. And, there's trillions and trillions of chemical reactions that go on in our body every single second. And the fact that they all happen to find each other perfectly and all work in this homeostasis is essentially what he said is flawed. There needs to be some sort of underlying structure, this essence, this energy, this understanding of the body greater than randomness. The randomness is so flawed, so flawed. We got to move past that. And really, even in quantum theory, it really made the random nature of biochemistry invalid. Like as you start to study like electrons and their movement, um, it's really difficult to kind of come to this random, like everything is just a random conclusion. It doesn't really make any sense. It's not grounded in physics, not even grounded in chemistry, for God's sakes. And a quote here I have is, molecules do not have to touch each other to interact. Energy can flow through the electromagnetic field, which, along with water, forms the matrix of life. And this quote here kind of depicts his work really well. That it's more energetical, right? It's more energy than physical molecules and nothing. These physical chemical reactions, the energy can flow. It can flow, right? So he also touched on a little bit of what he called cell water, which is also known as easy water or structured water. And it was really central to his work because the water being able to kind of build upon these proteins and conduct this energy and kind of expand the reach of proteins or whatever it may be, is certainly central to this opposite of the billiard ball theory. He proposed the macromolecule water interaction, so that these macromolecules, like proteins, are surrounded by these shells of structured water, structured by energy, which kind of increases the reach and increases the energetic field of the thing and provides a structure at the same time. So yeah, essentially the water around the molecules becomes the cell water, easy water, or structured water. These are all synonymous terms. And essentially that this structured water grows from surfaces. It grows from the surface layer by layer. And it layers and it takes on the charge of the innermost layer of the macromolecule. So you can see how this kind of expands the energetic field, right? And this is really getting into the energy of things, right? It's really getting more into the physics of the cell, of the energy of the cell. And an interesting question that he posed was, how do electrons know where to go? And this is funny because this actually came up in my undergraduate career and I thought of this. And so when I read this, I was just mind blown because I thought the same thing. When we were studying chlorophyll in the cells, which is exactly what he was talking about, it takes 1,000 chlorophyll molecules to split one atom of carbon dioxide. And interestingly enough, the electrons kind of bounce around like around the chlorophyll molecules, and they all have to cooperate perfectly. And the electron has to transfer from each and every single one of them. And obviously, we don't know the answer on why or how or whatever how that happens, right? So it's certainly greater than our understanding, right? And I think um, it's much more than the reductionist materialist view, right? There is this greater power at play here. It's absolutely obvious. You can dig as deep as you want, but there's always going to be that higher power at play, right? So, and the same goes with the electron transport chain. It's kind of the same thing. The electrons kind of know where to go. Again, there might be some nice flawed explanations out there. But then again, how foundational, how rooted in truth is it? I don't know. So Szent-Györgyi also proposed that organisms were alive due to the thousands of molecules from single systems with shared energy levels, such as physicists were describing in crystals. And I got this from the book The Invisible Rainbow, which is a great work on electricity and life. Again, another really foundational read, well written, long book, but well worth it. Get a lot of your money's worth. You get your money's worth for sure in that book. But yeah, essentially, like it was all about the energy of the body. And we may be chemical, our bodies may be chemical, but beyond the chemical level, there's an energy there. There's an energy in the atoms and the molecules. And essentially, the body shares this energy. So, the reductionist view of calories or of macromolecules and those ATP molecules and things like that, you can increase the energy of your body, the whole body, the energy of it, right? So, and that is a little more abstract, but it's still rooted in this idea that, as you increase the energy, you have more structure in the water. That's where you're holding the energy. There's more structure in your water, and you're made up of 60% water by volume, 99% water, more than 99% water by molecular count. Depends how you look at it. Increase the energy of your body stored in the water. You're going to structure your water. You're going to have proper cellular function. And so that was really really central to his thinking too, right? That these electrons are mobile. They belong to the whole system. They transmit energy and information over large distances, larger than just, the body itself. And what what I love is that he beautifully concluded that organic communication could not be explained solely by random collisions of molecules. And if there's anything that you can get out of this man's work is that the random collision of molecules is not enough. It's not enough. It's a reductionism, and it's not enough. And modern biochemistry lives and dies on the idea that that humans are random and godless, in my opinion. And I think that's terrible. All right, next here we have Gilbert Ling. He was alive 1919 to 2019, 100-year-old. Gilbert Ling did some amazing work. He's certainly technical. He's certainly getting into the nitty gritty here, but his work's really valuable. He kind of coined the association induction hypothesis. The structure and function of cells, membranes, are primarily governed by the association of water with proteins and lipids. So kind of built on Szent-Györgyi's work, but he was kind of looking at more from a cellular perspective, right? So Gilbert Ling kind of focused a lot more on the cell and focused on the shortfalls of the cell, which we're going to touch on here. Whereas Szent-Györgyi was more biochemistry based. So you can see how this was kind of building up here. So essentially, water molecules kind of interact with proteins and lipids in a structured manner, like I mentioned earlier, forming a dynamic and organized water layer that influences cellular processes. So, you have these layers of structured water on top of this of these proteins or these large molecules. And so the structuring of water and the selective absorption of ions and other substances at proteins play a crucial role in the cellular process, right? So having that structure around these proteins kind of helps in the proteins work. It helps in the work. So it's like ATP acts as a regulator for these phenomenon through induction, involving changes in electron density within the protein molecule and associated molecules. So you change and I know this is really technical, but when you change the electricity, when you change the energy of these macromolecules, you're changing the function, you're changing the structure, you're changing everything, right? So the energy is not separate from the chemistry or even the physical structure. That's why we can't reduce it to solely the physical. And this kind of led to the idea of phase transitioning, and so that these minute energetic changes can have major effects on the cell. So, these small, because our bodies are really delicate, we're very delicate electrical beings. And so, having these minute environmental shifts create large cellular responses, and that's really important to understand. Gilbert Ling also talked about the polarized oriented multi-layer theory, or structured water, more commonly known as, just that there's layers. The structured water acts as layers, right? Just layers of water. And so essentially the arrangement and interaction of molecules beyond the level of individual cells or organelles influenced cellular processes and contributed to overall cellular function, right? So it's all like every single detail is important here, right? The structure is important, the energy is important. It's all very important to cellular processes, right? And cellular function, right? And these small effects have absolutely major effects. And that's kind of this idea of this association induction hypothesis, that you can have these small effects, these small, delicate signals that create large processes, cellular processes, right? And so these cellular processes similarly can affect systemic processes. There's communication systems, so things act as one. And you can even go from systemic things to the whole body. Everything always acts as one. Even though everything's individual, we all act as one. You can see as above, so below. Gilbert Ling also talked about the sodium pump shortfall, which was expanded on by Gerald Pollack, who we're going to talk about next. Sorry, Harold Hillman before Gerald Pollack. I apologize, but we will get back to the sodium pump shortfall shortly. So Harold Hillman was alive in 1930 to 2016, and he proposed essentially that we should study live cells rather than dead cells. I know, a very absurd idea. He was most notably known for his proposed factors that altered cell life and their function and structures. Uh, so a lot of his work revolved around the electron microscope. Obviously, we went over those shortfalls in the last episode, but essentially that drying and freezing and altering the cell or altering the samples chemically affects the structure. It affects the function and the structure too, right? So even if you're going to look at the anatomy of something that's dead, it's not going to be the same as when it's alive. So one thing that he kind of talked about is that the endoplasmic reticulum is only present in dehydrated cells. And the analogy he used was a raisin versus the grape. So you wouldn't study a raisin to try and understand a grape, right? And the raisin being dehydrated. Because grapes don't have groves. So why would you measure the grove in the raisin to study a grape? That's the exact same analogy that he made with the cell, right? So that it's not about, with the cell, you dehydrate it and it becomes a raisin. How are you gonna figure out what a grape is from that, right? How are you gonna figure out what a cell is from a dehydrated cell? So I like that analogy. And essentially he proved that all seen under a microscope, an electron microscope, sorry, is merely an artifact. So everything is kind of just it's not what it actually is. It's just it's an artifact of that is the best way to describe it. And so the rebuttal is that why do all of the different techniques produce identical artifacts? Well, one, that's not necessarily true. But you can kind of answer this question like, okay, so we'll address the question, why do all the different techniques produce identical artifacts? Well, it's not necessarily true. First of all, it's not necessarily true. They don't always produce the same artifacts. But if they do, it's likely because you're using the same exact techniques. You're drying it, dehydrating it, staining it with the same chemicals, right? So you're doing the same process over and over again, so you're likely going to get similar artifacts. But his question, for the modern, or the skeptics to answer was, why do all of the cuts? Because you have to slice electron microscope samples extremely thin, and you have to take little slices of them. Why do all the cuts, which are random, right? You're not going to cut the cell in the exact same manner every single time in the same area. Why do they all produce identical images? And, my kind of interpretation of this is, why do they all produce identical images? Well, because the flat surface of the glass kind of acts as that foundation for the altered cell to adhere to. And so it structures off of this glass. And so when it structures off of this glass, you can even think of it from the association induction hypothesis that, since the glass is kind of the foundation, it's going to always build the same way off of that glass, and kind of structure itself in that manner. So it's complicated. It's Harold Hillman's work's quite technical as well. He did a lot of work on the brain, cellular function, things like that. And it's great if you like the technical stuff. I'd watch. There's a few of his lectures on YouTube that are really good. Um, but essentially, Hillman just proved that we got to study live cells, and he looked at the angles of things, and he looked at all the different stuff on why it's not the same as live cells, and the conclusion is just study live cells. It's not the same as dead cells. Same as a live person is not the same as a dead person. So Harold Hillman, he also looked at the rigid structure of the cytoskeleton fallacies. He didn't think that it allowed for the movement of organelles, which are mobile in the live cell, has been proven, which he proved as well. So he thought that the cytoskeleton of the cell is very dynamic, right? And this was kind of his theory. And this is kind of pushed more by Pollack or Tilney or Musker, that the cytoskeleton is dynamic. It moves. It's not this rigid, steel building, right? It's very dynamic. It can move because organelles need to move, right? And obviously the cell is highly dynamic. So that was also part of his work. And he also had this idea of subcellular fractionation, that there's a problem with homogenization and centrifugation. And obviously, centrifugation is used in viral filtration and its so-called isolation. And homogenization, of course, occurring a lot in dairy, which is a problem in dairy products. You don't necessarily want to consume homogenized products because essentially his idea was that it changes the entropy and the order, which fundamentally changes the chemistry. So when you change the order of things, it changes the chemistry, it changes the structure, it changes the energy. So that's an interesting idea as well. And so his work on the brain, 90% of the brain is made up of I quote here, a fine granular material that is virtually liquid. So, the reductionist model of the dead brain being the same as a live brain is kind of an absurd concept. Again, we don't understand anything about the brain, and what we do understand of the brain, a lot of it comes from the electrical studies of the brain, or it comes from cutting that brain open. So, it's tough. It's difficult. It's difficult to study this stuff truthfully and honestly. And there's no doubt about that. And it's not that every idea is absurd, but it's just difficult because it's difficult to study these things in depth. But then it comes down to the point, it's like, well, what is the point? What is the point of understanding this stuff more in depth? You can just go and live a long, healthy life. You don't need to know any of this stuff, really. Unless you enjoy it, then I guess you can learn about it. Then I guess it's not a waste. So Harold Hillman agreed with Ling's sodium pump shortfall, which we're gonna get into. It's a good one. And he was also against the idea of infectious disease. So yeah, I mean, it's just something to note. I mean, the people that really study the true structure of the body kind of have a greater understanding of the workings of the body, and of course, understanding you can kind of extrapolate that to disease, and so it's not it's obvious that he came to that conclusion, in my opinion. So I have a couple of medium quotes here from Harold Hillman. I'll read them out here, and I think they really summarize his work well. During a research career lasting more than 50 years, I have concluded that the following procedures are unsuitable for studying the biology of living cells in intact animals and plants. subcellular fractionation, histology, histochemistry, electron microscopy, binding studies, use of ligands, immunocytochemistry, tissue slices, disruptive techniques, dehydration, deep freezing, freeze drying, boiling, use of extracellular markers, receptor studies, patch clamp measurements, and inadequate calibrations. And in another quote here, the nuclei containing the nucleoli and the mitochondria are the only structures seen by light microscopy in the cytoplasm of living cells. All the other structures claimed to be present are only seen in electron micrographs of dead tissue or in fixed stain histological sections. If they existed, the cytoplasm would almost solid with endoplasmic reticulum, cytoskeleton, Golgi bodies, lysosomes, peroxisomes, contractile proteins, and stress fibers. So in both these quotes, obviously he went over what he disagrees with as being valid or invalid techniques, I should say. And in the second quote, he went over the basics of his idea of cell biology, and this is kind of the new cell biology that's being moved forward. And so he said the nuclei and the mitochondria, that's what can be seen in light microscopy in living cells. So, you know, hopefully we'll get deeper into this. I do want to talk about this deeper because just find it fascinating, the structure of the cell, and especially kind of dismantling the old model, which is important in itself. But I definitely think that both these quotes are very, very, very important for understanding not only Hillman's work, but the true state of modern cell biology and scientific procedures for that matter. All right, here we have Gerald Pollack, and fortunately, Gerald Pollack is still alive today. He was born 1950, and he's absolutely amazing. He's doing phenomenal work in this field. I really urge you to go and listen to Gerald Pollack's work. He's certainly well versed in Harold Hillman and Gilbert Ling and Szent-Györgyi and more and much more because this is a great field, a very large field that you can go quite in depth in and spend a lot of time looking at, especially if you're into the more practicing side of things, into the medical side of things. I think it's really important to understand the structures truthfully, to be able to heal them truthfully and honestly. So Gerald Pollack, obviously, structured water is his thing. He called it exclusion zone water, easy water. And he described this as being a gel-like consistency, higher density, and excludes solutes. It has a negative charge, and it acts as an energy storage. So that's the essential description physically of structured water. He wrote a book, The Fourth Phase of Water, which if you're interested in structured water, is it's amazing read. It's an amazing read for sure. So Gerald Pollack talks a lot about the role of easy water in mechanisms and functions of various biological systems, such as cell tissues and organs. And, it's involved in things like cell communication, cell membranes, cytoplasm, extracellular matrix, nutrient transport, waste removal, blood and cardiovascular system, nervous system, connective tissues, etc. And so it really opens the door for proper explanations of these things on the psychological or on the cellular level. Sorry. Um, and obviously he understands the impact of electromagnetic fields on the water, how our thoughts can guide the structure of water, and also how electricity can disrupt the structure of the water. And two people amazing in this field, Masaru Emoto, and Veda Austin, who's still alive today. She does amazing work on capturing pictures of structured water by placing intentions or objects in the water and seeing the shapes that the water creates. I would strongly urge you to check out that work. It's really, really impressive and it's beautiful. It's more like art than science, but what is science but an art? So the sodium pump energy shortfall. This is kind of a major thing because it was kind of the first thing that we learned in physiology. It was like it's like central. It's like the sodium pump, right? And so the shortfall here is that the pump energy needed in the cell to keep the balance of sodium and potassium requires 15 to 30 times the energy produced by the cell. So the cell can't keep up with the energetical demands based on the current modern model of the sodium pump. And it's likely underestimated for most cells due to the amount of pumps for each cell and organelle. So, it's like according to the modern models, we're 15 to 30 times short on energy, and that's solely if the only thing needed energy is the sodium pump. So it's just unbelievable. There's not enough energy to support this idea, and it's pushed. It's ingrained in us. It's the first thing learned in physiology. It's the first thing learned and so that just highlights the importance of understanding that because it doesn't align with physics. Um, it's not that they don't exist. The sodium pump, it's not like it doesn't exist. Like you can see like we know that the proteins are there. Um, but it likely just has different function, different purpose, not necessarily to keep the solute balance correct in the cell. And um, this was proposed by Link, obviously, the sodium pump energy shortfall. But Gerald Pollack talks a lot about it in his books, Cells, Gels, and the Mechanisms of Life, I believe. Look up Gerald Pollack's books. He has two books. They're amazing. Read them both. And so, even with this structured cellular model, like if you approach the body from the same way, if you look at the cardiovascular system, you know, the amount of energy that it takes to pump the blood through the entire body is much less than the heart can actually produce in pumps. So the pump of the heart falls short on energy. Now, this is explained beautifully by structured water because this energetical component allows for the sliding of blood to reduce the friction of the blood. Because if you study circulation through the physics lens, the heart cannot pump enough. It can't pump hard enough. So even the fact that through capillaries, the red blood cell is larger than the capillary. And so take a straw and try and blow a a marble through it. Well, good luck. And that's a straw man argument right there, and I'll acknowledge that. Um, because obviously it's more dynamic than that. Uh, but still, if you could consider that same argument without straw manning it, even though it's dynamic, it would still take a lot of force, right? So that's kind of how they calculate it, right? When you're trying to disprove this idea. Um, and so the amount of force it takes, it's impossible that the heart is solely a pump. And so Tom Cohen wrote a great book, Human Heart, Cosmic Heart. And he talks a lot about this and how the heart is not solely a pump. Yeah, it pumps, it beats, you can feel it. Um, but that's not its sole purpose, right? And so that's really important to highlight. And that the structured water is the proposed, it adds to that, right? Because it removes the friction, it removes the force needed from the heart. Um, which is important. Now, the heart is kind of a more of like an energetical vortex too, right? So that plays a role as well because, structured water obviously needs energy. And obviously the heart has been talked about for thousands of years, thousands and thousands. It goes back. It's so rooted in our psyches. The heart being an area of energy and love and things of that nature. So it's kind of interesting to think of it like that too, like how we had this great understanding of the heart and then reduced it to being a pump and to being this mechanism. But even that falls short when you study physics, right? So they pulled another fast one on us there. Another one is the nervous system. Now, Dr. Tom Cohen speaks of this as well, um, uh, because Dr. Cohen is very fond of Gerald Pollack's work, obviously because it's phenomenal. But within the nervous system, the modern the modern explanation is that one nerve takes 0.05 seconds to conduct. the charge across to go from one side to the other. And so if you have 20 nerves from your brain to your finger, and I tell my brain to move my finger, well, I can do it instantly, right? And if you calculate, if you add up this, 0.4 of a second, it doesn't take that long unless you have something seriously wrong with your nervous system. So, even in the nervous system, it's problematic. And I don't have an explanation on how structured water affects this, but it's just important to highlight that, even the nervous system has shortfalls, that we can't just reduce things to the materialistic view, right? We can't just reduce it to, oh, well, there's pumps and there's sodium comes in and the charge moves across and it's this big, beautiful chemical reaction that, oh, look, it's all just random and the billiard ball theory, right? You cannot just reduce it to that. It's not fair. Not fair to the body, not fair to the creator, not fair to Mother Nature. And so another important aspect of Gerald Pollack's work is the cell membrane, right? So, and this is kind of being dismantled over time too. Rather than cells being kept in by the membrane, it's the gel, it's the structured water of the cell, right? So the cell is not kept in by the membrane, um, because the membrane is not the structuring component. The membrane kind of builds on. And the membrane is just as much protein as it is fat. And in some, like in bacteria and even the mitochondria, it might be a 2-to-1 ratio, protein to lipid ratio. In some bacteria, or it's 5-to-1 protein to lipid ratio. So it's more, when you look at the lipid bilayer, you think, the models that they give us in physiology, which are just CGI descriptions of it, it's all fat when it should just be half protein at least, if not more. So it's a lot of protein, less fat than you think, right? You'd think it's the double bilayer of fat. So it's kept in by this gel. It's kept in by the structure of the cell, by probably the energetic house called the nucleus, right? So, these cells have these kind of their own energetical vortexes, right? And cells are dynamic and they move, and it's more like the easiest way is to explain it is more like gel than it is a rigid structure. It's dynamic. Everything is in motion always, always, always. And so, okay, so I'll get into a couple of experiments that kind of prove this point. So you can take a cell and remove a part of the membrane. So if the membrane model holds true, you remove part of the membrane, and ions like sodium or potassium should flow in, right? And it should disbalance the proportions of the cell. But you can remove the membrane off of a cell, and ions do not infiltrate the cell. That is an experiment that has been done. Ions follow proteins out in conglomerates because the proteins have this structure and this energy to it that ions may cling to. So ions follow proteins, and this only occurs 5 to 6 minutes after the membrane was penetrated. In eye cells, interestingly, it happens 8 hours after the cell was penetrated. In both cases, the holes in the membranes were detectable after 1 to 2 minutes. So you put the hole in the membrane. There are many ways to do this, electrophoresis or electrophoresis, I think is the word. And you can actually take a section out physically and and you can notice this hole, but guess what? The ions don't flow out because it's a gel. It's not this little vesicle like a cell that holds a bunch of water in, right? So ions always gather near organelles like mitochondria or endoplasmic reticula, which is also, a beneficial thing because they need these. There's a reason why we have these ions. There's a reason why we have these minerals in our body because proteins need them as cofactors. And obviously ions gather near proteins as well. We touched on to the 1-to-1 to 5-to-1 protein lipid ratio of the membrane. And so really, like I said, it's more of a protein structure with lipid inclusions. It's not a lipid structure with protein inclusions. That's the major fallacy here. And so what's the point of this? Who cares, right? The point is that, the membrane acts more like scaffolding for protein. It's more of just scaffolding. It's certainly more dynamic than anything. Um, you know, it acts more like a partial barrier, perhaps, for larger metabolites or soluble proteins, um, and perhaps a deflector of transmembrane ion flow. So, there is a purpose to having that structure there, but acting as the rigid walls of a cell is not the case. We'll touch briefly on Robert O. Becker, alive 1923 to 2008. He was an orthopedic surgeon and was super concerned with bioelectricity. He studied salamanders. He wrote a book, The Body Electric. Amazing read, amazing book, pretty easy to read. And essentially, what it is, he mimicked the healing electrical currents observed in salamanders, mimicked it in humans, and was able to heal fractured bones in humans and regrow bones. Um, Obviously, this was touted as ineffective by the mainstream, as meta-analysis disproved bone regeneration as being uncertain, was the conclusion that they dropped. And another study showed that there was a lack of randomized controlled trials. So, you know, if you're looking at it from that standpoint, you may discredit this work. Um, but he certainly had cases, whether you want to call them miracles or whether you want to call it done correctly. Um, that's an important distinction. So another, essentially, his work on energy in the body, he basically showed that there's an alternate electrical system in the body other than the nervous system, and this is kind of like the slow energy, more conducive to healing. So he proposed that these Schwann cells, or the myelin-containing glial cells, carry this energy. So that's part of the nervous system, but kind of like the insulators of the nervous system, if you want to look at it from a reductionist view. So not the nerve cell. Like, this energy is not nerve cells. It's a different part of the nervous system. Um, and it's likely that these kind of align with acupuncture meridians, right? So um, talk about energetics in Eastern medicines. This is likely the healing energy that they're talking about. And so essentially, he proved that electricity is conducive for growth, development, and healing and regeneration. And that's what salamanders use, right? So they have this inverted energy when they cut their tail off, and that's why they're able to grow their tail out. I really urge it, I'm really doing a disjustice to his work here. Um, by explaining it so brief, but his book is phenomenal, The Body Electric. Um, I'd highly recommend you to read it. And finally, right, he viewed bones as semiconductors as well. So they kind of used the copper, and they're piezoelectric, which we'll talk about in the next lecture. But yeah, so bones carry an energy as well. Okay, and finally, I have two gentlemen here. Peter Deusburg, who is still alive today. He was born in 1936, and Kary Mullis, 1994 to 2019. Now, these two gentlemen here are kind of the two first that I got into, and they did their work primarily with AIDS. Deusburg is a German-American author of inventing the AIDS virus. He questioned basically the scientific evidence supporting the link between HIV and AIDS, and criticized the use of antiretroviral drugs in AIDS treatment. And he proposed that HIV is a harmless passenger virus, that AIDS is caused by other factors such as drug use, malnutrition, and lifestyle choices. And so AZT was the drug used. He also explored how AZT was likely causing a lot of AIDS cases as well. And people took, they kind of took the drug preemptively too, if they were, under doing lifestyle things which were thought to promote AIDS. I think we can all, I think we all know what I'm talking about here. I don't got to say it, but the book is great, and it was one of the first books that I read. And really, he talks about Anthony Fauci a lot, and how he was just a politician and just virus hunters, and and kind of the field of virus hunting. And I think it's a really important read if you're getting into this field because it kind of shows how, the establishments kind of push this notion of germ theory. So I think that's important to read. And Kary Mullis was actually he did the foreword for the book, did a great foreword. And Mullis is actually the inventor of the polymerase chain reaction test. He did it in 1983. He got a Nobel Prize for this, obviously. He's a Nobel laureate in chemistry, 1993 for the PCR test. And he questioned the direct causative relationship between germs and diseases, of course. He highly doubted the link between HIV and AIDS. Um, he attributed disease more so to factors such as genetics, lifestyle choices, environmental factors, and immune system function. So, Kary Mullis wasn't a full-blown germ theorist or, germ theorist or terrain, theorist either. I think if he would have lived through COVID, I'm sure he would have certainly came to the correct conclusion there because there's a lot of people talking about it now where it hasn't been out in the open, talked about a lot lately, until lately. But he expressed interest in various alternative and holistic approaches to health and disease treatment. Kary Mullis, spoke out about the use of polymerase chain reaction in diagnosing people with infectious diseases, like in AIDS, and that's why I say AIDS is the first version of COVID because that's when they started to use PCR. Um, and so they use the PCR in the COVID, obviously, to push cases, but really, it's an inconclusive way. It's not a gold standard test at all. And it can be abused if you look at the cycles, but we'll touch on that when we talk about COVID in the next one. And okay, here I have a couple of honorable mentions of people through history. Florence Nightingale, of course, alive 1820 to 1910. She spoke out against the germ theory and disease classification fallacies. And so her work is really great. She was a nurse and known as maybe the most popular nurse ever. Another good one, Wilhelm von Bremer, 1883 to 1958. He was a biologist, did a lot of work in dark field microscopy, pleomorphism, touched a little bit in plants, actually, which is interesting. You don't see too many people in this field looking at pleomorphism in plants, only briefly. He did look at it as animals as well. Another good one to study is Hans Selye, alive 1907 to 1982, and he did a lot of work on stress. Um, and it was really interesting. He was actually in his book The Stress of Life in 1956. He's the one who said Bernard was right, the microbe is nothing, the terrain is everything. The quote that's often attributed to Louis Pasteur, Hans Selye said it, and I think that's really important to distinguish. But yeah, so he was certainly on board with the idea that the terrain is everything, and his work on stress is really good because that's one thing that you do see in people in long-lived individuals is they live low stress, no stress, low stress, able to deal with stress properly. And I think that's really, really important to longevity. We talk a lot about these specifics and biomarkers and genetic factors and lifestyle choices. And the biggest choice is to live a less stressful life, I think. I really think that's central. Obviously, other factors have things to do with it, and, avoiding toxicity and maximum nutrition is important. But if you understand that the energetics of the body is everything, keeping your energy in order will allow you to order your body because biology follows energy. So, focus on your energy, focus on stress and things of that nature. And finally, I got to mention Dr. Harvey Bigelsen, alive 1940 to 2019. He did a lot of work in dark field microscopy, a lot of work on blood. He was a hands-on guy, worked down south, and he was phenomenal. His two sons now are really carrying the torch, and yeah, they're doing amazing work as well. I'd love to get them on the podcast and perhaps in the future. Uh, because yeah, Harvey Bigelsen was absolutely amazing, an amazing practitioner. All right, and I'll mention a few of scientists that are currently alive that I believe are true, honest scientists. There's Dr. Stefan Lanka, a virologist, Dr. Bear Lando, doing alpha cast, kind of out of the practicing field, but really pushing this bioterrain model forward and really educating a lot of people. Dr. Tom Cohen, currently doing the new biology curriculum, so he's really pushing this new biology as well on the new structure of the cell and obviously the terrain model. Dr. Andrew Kaufman, a lot of work in exosomes, same holistic type thing. Absolutely amazing. These four guys are really, really top of the field, in my opinion. There's doctors Sam and Mark Bailey. They do amazing work generally in this field. Dr. Gerald Pollack, cell structures and things of that nature, structured water. He's amazing. Adam and John Biggleson, I just mentioned, doing great work. Veda Austin with her work on water. I would check into her work. It's absolutely amazing. Sally Fallon Morale, working with the Weston A. Price Foundation. She does great work on nourishment and obviously just generally as well. I really like Robert Edward Grant's work. He does great work in kind of biogeometry in that area and trying to decode history's secrets. Another great one is Daniel Riota's from the Humanely podcast. He does great work as well. He's really pushing some new ideas, which I think is really, really important and challenging a lot of the old notions. Even he does work with vitamins and nutrients um he really allowed me to understand mold in a better light too. If you're concerned about, oh well, mold seems to cause a lot of disease, well, he's your guy to look into for sure. And there's a lot of truth seekers out there. You don't have to be a doctor, you don't have to be a scientist by trade to be able to understand this kind of stuff. Like, if you're interested in it and you just read about it and learn about it yourself, like, and you have a genuine urge to seek the truth, well, the truth shall reveal itself. And yeah, don't let, like, I know it's technical, but don't let that hold you back. Like, these are certainly more technical. These podcasts are more technical than one I anticipated, and two than maybe I'd like them to be. But I think they're setting a good foundation for what I'm going to talk about moving forward. And moving forward, I do like the technical aspects of things. But I certainly want to ensure that I have concrete, pragmatic ways of dealing with things like being healthy and preventing disease. So, um, like I said, if you want to look into more like the concrete ways, I post a lot more of that on my Instagram than in these long-winded, um, podcasts. So, in the next one, we're going to talk about the state of the body, right? So we kind of touched on that a little bit. We kind of touched on it from the perspective of who was kind of bringing these ideas to light. We'll kind of bring it all together and talk about the body as an electric being. We're going to talk about some terrain perspectives. So we're going to talk about things like the cause of disease, symptoms, diet, immune system, parasites, Lyme, tetanus, and kind of the terrain perspective on these, kind of not necessarily redefining, but really looking at them truthfully and what they are in naturally. And we're going to cover some of the demics, epidemics, pandemics through history and propose alternative um, causes for those. So things like the Spanish flu or polio or even AIDS, COVID, and more as well. And we'll touch on kind of their causes, right? So that'll be in the next one. Guys, thank you so much for listening. Another great episode. The next one, I'm so pumped for the next one. Like, we're really getting into the nitty-gritty, and then we're gonna get some guests on. I want you guys all to remember, this is not medical advice. This is for general informational purposes only. But also remember that we're responsible for our health. We're responsible for everything in our lives. We're sovereign. We're capable of thinking and criticizing and understanding everything. We, the people, and the greater forces are together self-healers, self-governable, self-teachers, and so much more. Please reach out if you have any questions, comments, criticisms. Reach me at beyond.terrain on Instagram. And listen, I truly appreciate every single person that took the time to listen today. I appreciate all the feedback I got in the last couple podcasts, and it's really helped me motivate me to continue on and put a lot of effort into this, and I love it. Like I love talking about this stuff. I could go on about it all day. So if you enjoyed the podcast or found it informative in any way, please like, share, comment, support me and help me grow. Remember, there are two types of people in the world: those who believe they can, then those who believe they can't. And they're both correct. Thanks for listening. Take care.